We are continuing part 2 of constraint optimization consumption equilibrium for week 4. So on slide 8, you are told how you will be assessed in ECO235. So you will be asked to calculate which bundle of good X and good Y will maximize an individual's utility subject to the budget constraint, because there is a constraint now, as opposed to last week where you looked at unconstrained optimization problems. So you, in essence, need to determine X and Y and also the total utility of the function. So here is an example. You are told, suppose the utility that Mary receives by consuming food, that is good X, and clothing, good Y, is represented by the utility function U is equal to xy, the product of xy. So again, here you're told that food is going to be denoted by the letter X and clothing is Y. But if you look at the utility function, if you weren't given the symbols or the variables X and Y and it was something else, the first coordinate would always represent what is on your horizontal or X axis, and the second would represent what is on your vertical or y-axis. So now you are further told that food cost 1 Rand per unit and clothing costs 3 Rand per unit. So there's your price of good X and your price of good Y. And Mary has an income of 12 Rand to spend on the two goods. Now, this is a very straightforward example. Your applications will be more complicated than this, but the process is exactly the same. So firstly, you can derive Mary's budget constraint, and that can be done by taking your price of good X times X. This is what we'll need to determine, plus the price of good Y times Y is equal to the income. So you can substitute the values that you have. Now note again, your budget constraint is linear, and you know that the equation for a straight line is Y is equal to mx plus c. So therefore you can rearrange to make Y the subject of the formula, and you can clearly see that your gradient m, or the coefficient of x in this case, is going to be given by minus a third, right? Which you can also deduce by looking at the ratio, the negative ratio of your prices. So the price of good X was 1 Rand and the price of clothing, good Y, was 3 Rand. So 1/3 is a third, and it's the negative ratio of the prices. So that is just rearranging, making Y the subject of the formula. There is your slope of your budget constraint. So what is the slope of this line? It is minus 1/3. Next, your marginal rate of substitution, it is the ratio of your marginal utilities. So that is the negative ratio of your marginal utility of X over the marginal utility of good Y. So now you need to perform partial differential calculus to solve for each first order partial derivative. So therefore, to derive the marginal utility of good X, so this notation, if you say mux, I know that this is the first order partial derivative of your utility function, or you could say your partial derivative of your utility function with respect to x, it is equal to y. So if we just go back to the previous slide, remember your utility function was just xy. So if I get the partial derivative of this utility function with respect to x and I treat y constant, remember this is going to be 1 times the coefficient of x is 1 times x raised to the power of 0, which is just 1. So what you're left with is, because this is a constant multiple, when you differentiate, you get your first order partial with respect to x, you are just left with y. And similarly, if you get your first order partial derivative of the utility function with respect to y, treating x as constant, similarly, you're just going to be left with x. Right? So your marginal utility here, to derive your marginal utility of good y, treating x as constant, your first order partial derivative of your utility function with respect to y is just going to be equal to x in this instance. So therefore, What is the utility maximizing choice of food and clothing? So that occurs where the two slopes, the negative two slopes are equal. So that is your marginal rate of substitution, which is the ratio of your marginal utilities, is equal to the ratio of your prices or the slope of the budget constraint. Right? So this is your equilibrium condition. So if we equate minus y over x equal to minus a third, you can now determine what that utility maximizing choice of food for clothing, or in essence, what is that optimal bundle or mix of the two goods. So we haven't solved for x or y yet. This just tells us what the optimal bundle is. So of course the negatives will cancel. So you could either rearrange such that you can say y is going to be equal to a third x, or you could rearrange such that x is equal to 3y. Either way, it is fine. So what do we do with this optimal bundle mix? So we're going to substitute that into the budget line equation. So this was your budget line equation. If you substitute x is equal to 3y, now you find that by solving simultaneously, you have eliminated one unknown. You can now solve for y, and y is going to be equal to 2. And you can now take that back into there, and 3 times 2 is similarly going to be equal to 6. So x, in this case, if we substitute y is equal to 2 in over there, x is equal to 6. So we have our combination of y and x, and to determine the utility level, remember your utility function was just the product of x and y. We now have x and y, so 6 times 2 is equal to 12. So this is a fairly straightforward example, just in terms of the math or the algebra behind it. Here's another example. Max has the utility function xy plus x, and the per unit price of x is $2 and the per unit price of y is $1. His income is $10. So how much x does Max demand and how much y, and what is the utility level? So follow the same process as you did in the previous example. So previously we first got the budget constraint, but this question doesn't set out each step in terms of what you need to do first. So if you first get your MRS and then your ratio of your prices and then your budget line, that is fine. So first off, we're obtaining our marginal rate of substitution, which is given by the ratio of my marginal utility of good x over my marginal utility of good y. So my marginal utility of x is the first order partial derivative of this utility function with respect to x, treating y as a constant. So if I get my first order partial derivative of this with respect to x, I'm going to be left with y plus 1. Because if I differentiate x here, I'm just left with y. Plus, if you differentiate x, you're just going to get 1. So this is y plus 1 when you get your first order partial with respect to x. Now, if you get your first order partial derivative with respect to y of the utility function with respect to y, treating x as constant, this is just going to be equal to y. And remember, you're treating x as constant, so this differentiates to 0. So this marginal utility of y is just equal to x. Hence, your marginal rate of substitution, which is the ratio of these two, of course, it is the negative, and the negative was dropped earlier on in this example, but for correctness, you should keep the negative. It is going to be y plus 1, that is your MUX, over your marginal utility of y, which is x. So that is your MRS, and your ratio of your prices, which is the slope of your budget constraint, is just equal to 2. So how did we get that? The price of good x was $2, and the price per unit of good y is $1. So 2 over 1 is just 2. So now we can equate that, because at the point of tangency or equilibrium condition, my MRS is equal to my ratio of my prices. So if we equate the two, there you go. They are your negative ratios of these two. So I am going to rearrange again such that either y or x is the subject of the formula, so that I can obtain my optimal bundle or mix, which I'm going to substitute into my budget line equation. So I'm going to multiply both sides by negative x because x is in the denominator. That will get rid of that. So I will end up getting y plus 1 is equal to, although I don't have the step, is equal to 2x. So hence y, if I take the plus 1 over, it will become y is equal to 2x minus 1. So I can now substitute this into my budget line equation where I have the y. So therefore, if I have y is equal to 2x minus 1, and I'm substituting this into my budget line equation, it will become 2x plus, there's the y, substitute this 2x minus 1 for the y, equal to 10. So now if we just check our signs, that will become plus 2x and that will remain minus 1. So therefore you will have 2x plus 2x is 4x, and you take the minus 1 over, you're going to have 10 plus 1 is 11. Hence x is going to be 11 over 4. And if you're going to take this and substitute this back into either one over here, you can then solve for y, and y is going to be equal to 9 over 2. Just by taking x is equal to 11 over 4 and substituting it into this optimal bundle, you can determine what y is equal to. Now you have x and y, which was the first part of the question, and you can substitute those values into your utility function that you were given at the start of the problem, and carefully substitute, and you can solve for your utility. So in the previous example, you can test this on your own. For max, if income now increased to 20, so always read carefully, it's not by 20, it's to 20. Calculate the quantity of each good consumed as well as the utility level. So of course your budget constraint is going to change. So the only thing that will change is instead of this being 10, it will become 20. And then you can rework and determine your new x, y, and utility level. And the answers are given as 5.25, 9.5, and 55.125. You can check this when you work through these examples in your own time. Lastly, these are the following homework exercises that you should attempt before I upload the answers. And these are the 2 examples. So notice now you are given slightly more complicated utility functions where you have exponents. So please be careful when you work through these 2 problems, when you get your first order partial derivatives of your utility function with respect to good x and y. Be careful with how you operate using these exponents. You need to revise your rules of exponents. That concludes your constraint optimization. The solution to these 2 problems are given below. So this is the solution to question 8 above, and the answer to question 9 is given below. So while you have your values for x, y, and utility, you still need to work through these problems and arrive at these answers so that you can assure yourself that you know how to solve this type of problem. I thought to give it to you primarily because these exponents are a little bit tricky. So this concludes constraint optimization.